Hi, my name is Jeff Davis, and today I'll be talking about Citus Columnar. Citus Columnar is a columnar compression feature that comes with Citus. Citus is fully open source, and it's a pure extension, so you can use it on unmodified Postgres. You don't need anything special. Columnar arranges data by column rather than by row. So data across many rows from the same column is all stored together, improving compression, and it also enables skipping past unnecessary columns that aren't mentioned in the query. The benefits of Columnar are clear. Lower storage requirements, because obviously it's compressed. Less I/O, again because of compression, but also because of projection pushdown, which is where we skip past those unnecessary columns that aren't needed by the query. These lead to faster scans because there's less I/O. There's also a feature called chunk group filtering, which I'll talk about later. Let's check it out. First, make sure that Citus is in the shared preload libraries list. Next, create the Citus extension. It's already created here because I preloaded some data. Then we can create a simple columnar table. Notice this using columnar clause. This is what tells Postgres that our table is going to use the columnar access method, which is defined when creating the Citus extension. That allows Postgres to hook into all of the custom code that we've written in our extension to handle the columnar storage format. We can insert a couple of simple values. We can also copy, but we can't update or delete. Now let's look at a more interesting use case. Columnar works best in combination with range partitioning, especially time-based range partitioning. The idea is to keep the newest partitions as row tables so you can update and delete those newer partitions. But older partitions, you columnarize, you turn them into columnar tables in order to improve the scan speed and also reduce the storage requirements. Let's see this. Here, I'm creating a simple partitioned parent table. Notice that I'm partitioning by the timestamp. Also notice that I didn't specify a using clause. The partition parent doesn't hold any data, so specifying a table access method doesn't make any sense and is in fact disallowed. Now let's create a partition for January. Here I do specify the using columnar clause, and that will be a columnar partition. Now, let's create a partition for February. But here, let's use a row store, the default using heap. Now let's insert into the parent. For January, and for February, we can see that interacting with the parent seamlessly reads from both the columnar and the row store partitions just fine. If we try to update the parent for some values in the January partition, that's columnar, so we'd expect this to fail. But if we update where the timestamp falls in February, it works just fine. We can again select, we can see our update. Now, let's create a partition for March. That's going to be a row partition again. So we have January is a columnar partition, February is a row partition, and March is a row partition. You can see that with piece equals describe. Columnar. Heap. And heap. Now let's say that we've decided that we're done with February. Maybe there's a lot of data in there, and we don't want to update or delete it anymore. Instead, we'd like to save on the overall space consumption and improve scan speed for the month of February. We can do that with a provided UDF. This performs the magic while avoiding excessive locking to transform the table, the given table, which could be a partition or an ordinary table, to transform that into the access method provided, which in this case is columnar. This function comes with the Citus extension. Of course, if there was a lot of data in the table, changing the format will take some time, but here we just have a single tuple there, so it happened instantaneously. The function tries to avoid excessive locking, so in the case of partition hierarchy, it doesn't cause too much interference with the rest of the system. Now, we can see that the February partition is now columnar. We could see a couple limitations there. So no update and delete for columnar, of course. Columnar is append only. Use insert or copy to load into the columnar table. There's also no logical replication or logical decoding yet. only B-tree and hash indexes are supported. And there are a few more feature gaps, and hopefully we'll close those in the future. Now let's look at the compression and I/O savings that we get out of Columnar. The compression, of course, saves on storage and I/O, and the projection pushdown saves on I/O again by skipping over those unnecessary columns from the query. There are two preloaded tables here. One that's a row table, other is a columnar table. They both have exactly the same data. 5 million rows, and they're 100 columns wide. So we're talking about a wide table with a medium-sized amount of data. First, let's look at the total relation size of the row table divided by the size of the columnar table. We can see here about an 8x compression ratio. Running vacuum verbose on a columnar table tells you a little bit more information. Chunks are a unit of storage in columnar. You can see there are 50,000 total. And out of those 50,000, all 50,000 are compressed using the Z-standard compression algorithm, which we found to be a good default. You can also use LZ4 or other compression algorithms. The compression rate here is calculated a little bit differently, but it's a similar number. Now let's look at the total number of blocks in the table. In the row table, there are about 550,000 8K blocks. In the columnar table, only about 70,000 8K blocks. Now let's run explain analyze on the row table. This is a group aggregation query. And we can see in the results that it needed to read, one way or another, all 550,000 blocks. Some of them may be hit in shared buffers, maybe more if you have larger shared buffers and a warm cache. But the point is, row store, we'd expect it needs to touch every block to read that data. Let's run the same query on columnar. Here, we can see it only needs to touch 6,000 blocks. That's 2 orders of magnitude lower than for the row table. The first order of magnitude comes simply from the compression. Row table has 550,000 blocks, columnar table only 70,000 blocks. The second order of magnitude comes because out of those 100 columns, we're only projecting 3, and columnar is able to skip over those other unnecessary columns. Those combine together to give us a 2 orders of magnitude improvement in terms of how many blocks need to be read in columnar versus row. What about indexes? Columnar supports B-tree and hash indexes, which is important because if you define an index on the parent of a partition table, then all the partitions, row or columnar partitions, must create that index. It also enables the use of unique constraints on a columnar table. But indexes take space too. Although the columnar data itself is compressed, the indexes are ordinary Postgres indexes taking the same amount of space they would on a row table. So you don't want a situation where you saved all this space by compressing the columnar data, but then the indexes prevent you from really realizing as much savings because those still take up a lot of space. That's where chunk group filtering comes into play. Here I'm going to show a table T with no indexes on it at all. It's in columnar format, of course. This is a very simple table, and it's got 100 million tuples, a single column of type timestamp. And these 100 million tuples are just timestamps spread 10 seconds apart over a long period of time. We're going to run this query on it, which is a simple count of the tuples that fall within this timestamp range here of a single day, January 1st to January 2nd of 2020. Again, this table has 100 million tuples and no indexes. How did it execute so fast? It only took 143 milliseconds. Well, the answer is something called chunk group filtering. A chunk is a unit of storage in Columnar that represents 10,000 values. This table consists of 10,000 chunks because 10,000 chunks times 10,000 values equals 100 million tuples overall. So the entire table consists of 10,000 chunks. But how many of those chunks were removed by filter? It actually removed all but 2 of those 10,000 chunks with the chunk group filter. It didn't bother to read those chunks at all, let alone decompress them. The way it was able to do that is by applying this predicate from the where clause to simple min-max metadata kept for each chunk. If the min and max and the where clause were incompatible, it simply wouldn't bother to read the chunk or decompress it or do any other work. It would simply go on to the metadata for the next chunk to find out if that chunk should be read or not. The end result is that out of 10,000 chunks, only 2 chunks were actually read. Then, out of those chunks, 2 chunks that were read, an ordinary Postgres filter removed another 11,000 tuples. That was done normally, there's no special optimization there. And then after removing those 11,000 tuples, then we're left with 8,600 tuples, as we'd expect for a single day of timestamps spread across 10 seconds apart. So again, chunk group filtering is based on this unit of storage in Columnar called a chunk, each one holding 10,000 values by default, and it's able to use Columnar metadata to exclude some of those chunks before it bothers to read them, thereby saving on all of that I/O. Chunk group filtering works very much like an index, but there's no index required. It uses the metadata for the columnar table, and it's automatically available for every column of every columnar table. It's based on min-max, and conceptually it's very similar to a Brin index, but Brin indexes are based on pages, which don't apply perfectly to the columnar storage format. So we specialize this concept for Columnar itself, track the data separately in our own metadata, and then use that to conceptually do something very similar to Brin index, but without the need to define it. So how did we do this? This is PGCon, so this is the hacker portion of the talk. We used a lot of extension APIs that made this all possible by tightly integrating with Postgres. With enough code, it seems like you can do almost anything with an extension. First, at the core, are table access methods. This is an API that allows a custom storage format to behave just like the built-in heap storage format that's based on rows. So even an entirely different storage format like Columnar, we can see how it interacts in much the same way as an ordinary row table. Of course, Columnar has a few limitations, such as updates and deletes that don't exist for a row table. You do this by defining dozens of methods related to the table access method API. These do things like define how a scan should work, how a vacuum should work, inserts, index lookups, everything. And if you define all of these, then you get this great benefit of integration with the rest of Postgres. So you don't have to worry about things like PG dump or PG upgrade working. If you define all of these things properly, then those will work for you right away. The next piece of the puzzle is custom scan. This is the planner and executor integration. This is what allows things like the projection pushdown, which skips over the unnecessary columns, and the chunk group filtering to function. Custom scans will often go with table access methods. Thirdly, we made use of generic wall. This records arbitrary page changes in the write-ahead log and enables crash recovery and physical replication to work easily. Unfortunately, generic wall doesn't work with logical decoding or logical replication. So, coming soon in Postgres 15, we introduced a new extension API for defining an entirely new custom wall resource manager. This enables extensions to define their own custom write-ahead log record formats, as well as redo and decoding routines, and that enables full control of the extension over write-ahead log and enables logical replication and logical decoding to work, in addition to recovery and physical replication. There's also prototype support in Columnar for making use of this custom wall resource manager API that can demonstrate logical replication and logical decoding functioning as normal. Process utility hooks. These allow intercepting arbitrary utility commands and doing pre-post processing or error checking. Can also even modify the utility commands that are passed in. It's a bit hacky, but enables some nice workarounds in lots of cases that can't be handled otherwise. Sometimes just error checking is useful. We use it in Columnar for error checking, for instance, unsupported operations, unsupported index types, that kind of thing, allowing the ability to create a better error message. Object access hooks. We use these in Columnar to clean up metadata when a table is dropped. So when a table is dropped in ordinary Postgres, it's already got its built-in cleanup operations that need to happen. But for Columnar, we additionally needed to clear the metadata, and we're using the object access hooks to do that. We used custom GUCs. Almost every extension uses these, but if you didn't happen to know, you can define in an extension your own ergonomic configuration by defining custom GUCs that work with alter system and every other part of the system. It's just a really nice way to configure an extension that integrates with the rest of Postgres. So go out, download Citus, install it, and try out Citus Columnar. Thank you. Now for Q&A.